Our lesson for today will be looking at chemistry 1502. The topic for today will be looking at Williamson Ether Synthesis. Lesson 101. Let us start. Before we can get to the synthesis of ethers, let us quickly review what is an ether. Remember that on the introduction lesson video of ethers, we've talked about the general formula as we have an oxygen that has two groups, or we can say it separates two groups, or attached to two groups on both sides, from both sides. And those groups can be an aryl group or an alkyl group. We've also talked about the IUPAC naming of the ethers, which is an introduction. There is a lesson video whereby you continue with the practice question of the IUPAC naming. In this lesson video, we'll be looking at how to create these ethers. There are two ways to generate ethers. We can either use the dehydration of alcohol, or we can use Williamson synthesis. And today's lesson, we are going to be looking at the Williamson synthesis. Williamson synthesis is very simple. We are just going to take an alkoxide. We are going to react it with a haloalkane or an alkyl halide. The general mechanism for that is our alkoxide reacting with an alkyl halide to form ether. And we have our halide ion. Basically, we are going to have a back attack by the alkoxide and the leaving group. And by the way, this is a SN2 mechanism. Williamson uses SN2 mechanism. But this mechanism doesn't start from here. The initial step, or the first step, we generate this alkoxide ion. And how do we generate it? Alkoxides are created by reacting an alcohol with a metallic, sodium or potassium, or a metal hydride. So what we normally do, we take an alcohol, we react it with sodium, potassium, or sodium hydride as our metal hydride. This is the most common metal hydride that we use to create alkoxides. And then we get this. Then from here we take it, we react it with an alkyl halide to form an ether. For us to understand this mechanism very well, let us jump straight to our examples. Normally the challenges that we face with my students, the challenge is not the content itself or the question. The challenge is how they structure the questions. So in this case, you can see that we have this part here. Just note that the first reaction will be the numerator level, or on top of the arrow, and then after the product, we react the product with the second reaction. We have two reactions in the same equation, we can say chemical equation. So this was a challenge. So I believe starting from now on, we are not going to have a challenge. And once you get a question like this in one of the question papers or one of the exams, don't be confused. You simply react this with the first reagent or the first reactant and go to the second reaction with this part here. So we have an alcohol. We are going to react this alcohol with our metal hydride, and then once we get the product, we are going to react it with this alkyl halide. So the first step, what will happen is that this hydrogen from the metal hydride will actually react with this hydrogen from our alcohol. They will form H2, and then H2 will simply evaporate. And then our product, we are going to have, I'm going to use black for the first reaction. So the product of the first reaction, we are going to get CH3CH2, CH2, and then we only have oxygen. We no longer have this. And then it will be negatively charged, and then we are left with our sodium, which will be positive. It's actually sodium ion. And then this H2 will simply evaporate. And then we have to react this with our second part, which is CH3CH2Br. And if you can check, this is the beginning of the Williamson synthesis, because this is an alkoxide reacting with an alkyl halide. So what happens is that this alkoxide will back attack our alkyl halide, and then Br will leave. Let me actually use this method to represent this, because it's very important to represent the movement of electrons. So this will back attack. By the way, this is the nucleophile. This will be our substrate. So the alkoxide will attack, and then there will be the leaving group will leave to form our product. I'm going to use blue for the second reaction. So we still have this part, and we have our oxygen. Then we have CH2, CH3 plus Br. We can say this Br will simply react with this just to give a stable reaction, but you can see that this is our ether, which is our product. Let us go to the second second example. Our second example, it involves a cyclic structure, which is cyclohexanol. So we know that the first reaction is to create the alkoxide. So the product of this, we are going to have by the way, this, it also serves as the metal hydride, but it uses a different mechanism whereby it donates electrons to hydrogen to form hydrogen radicals and repeat the very same process to form at least two equivalents of hydrogen, and then they form our hydrogen gas. But at the end of the day, it will form our alkoxide. Then from here we have to take the alkoxide to react with our alkyl halide. And by the way, this OTS, it stands for tosylate. Some say it's tosylate. We can say it's a very complicated structure. That is why we simply abbreviate it with OTS. The structural formula of tosylate is like this. You simply put CH3, then we have sulfur with double bond, then we have oxygen, and then we have our R. Our R, it can be any group, it can be an alkyl halide. In this case, by the way, we have part of, sort of like it's a phenyl. Remember that phenyl, it's C6H5. The moment you see C6H5, just know it's a phenyl. normal like this, and then if you put hydrogens, you'll see that you'll have 5 hydrogens and 6 carbons. This is the molecular formula of phenyl. So you can see that this part is a partial part of phenyl, and it has the methyls and sulfur and oxygens. So this, it's a structural formula of a tosylate. So as you can see how complicated it is, we simply abbreviate it with the OTS, and it's our living group in this case. So our nucleophile will attack electrophile, and the living group will leave to form the structure oxygen, and then we are going to have yes, and the name for this we can say is the parent chain, and this has to be our substituent, our branch. So it's ethoxycyclohexane. Let us do the next example. And if you can check most of the reactions, the alkyl halide must be at least a methyl halide, a methyl halide, primary halide. Those two are most favorable because Williamson Ether Synthesis, it uses the SN2 mechanism. So remember that the substrates which are most suitable for the SN2 are the methyl halide, primary alkyl halide, and a bit of secondary alkyl halide. Okay, this should be sodium hydride. So the first reaction, we know that our hydrogen from the sodium hydride will react with this hydrogen to form H2 and evaporate. Then these 2 electrons will move to this oxygen. With 2 extra lone pairs. And then we take this, we are going to react it with the alkyl halide, the alkoxide. Let me actually write it like this. It's H3CI. Then it will attack the electrophile. And then we have our living group leaving the substrate to form and looking at the IUPAC name for this, we just have to go for the lowest number as possible. So this will be 1, 2, 3, 4, 5. So the parent chain will be pentane. We have pentane. On carbon number 2 we have our, this is methoxy. And then on carbon number 3 we have 1 comma, it's 3.3, the dimethyl. Then the IUPAC name will be 2-methoxy hyphen 3,3 hyphen dimethyl pentane. It's one name. Make sure that there's no space between this and the dimethyl. Our example number 4, it involves a phenyl. Just know that phenyls, we normally react them with sodium hydroxide. The protonation of this hydrogen of a phenyl, we use a sodium hydroxide, not a metal hydride like the other alcohols. And by the way, phenols and alcohols are different. That is why we are using a different reagent. So in this case, this OH will protonate this hydrogen, and the bond will go to our oxygen. And then for the second reaction, we are going to react it with a methyl halide. There will be an attack electrophile. To form our ether. The synthesis is very simple. You don't have to be confused. Let us look at example number 5, the last example. Let's say we have this type of an alcohol. The first reaction, we are going to react this with a metal, and then secondly we are going to react it with our alkyl halide. The first reaction, which is reaction number 1, will yield an alkoxide, with a negative charge, plus sodium ion. Then we take we react it with our alkyl halide. It will back attack the leaving group will leave to form if we're interested to name this would be the substituent, and we have how many carbons? We have 4 carbons, so it will be butoxy. Our numbering will start here. To have the lowest number, we're going to start here. So carbon number 1, we have 2 methyls, and then carbon number 3, we have our butoxy. And then we have what we have, or it's a cyclo, we have 6. So alphabetical order, B comes first compared to M. So we have 3 butoxy hyphen 1,1 hyphen dimethyl cyclohexane. We don't have any double bond. So this is the Williamson synthesis, Williamson's ether synthesis. Always, each and every lesson video, especially the introduction lesson video, there is a practice question lesson video whereby we look at more questions, or let me say more examples. That's it for this lesson video. This is Rahula SJ. Thank you very much.